Swayam Prabha. Digital India. Educated India.
So, my lecture is a little bit different than what you have already been told here. I wanted to show you some application of chemistry. You know, across the globe, the richest people are the petrochemical industries. Okay? The petrochemical companies are the richest people in the world. Not Elon Musk, they are even more than that, much ahead of Elon Musk. So, they have different products which they sell. One is crude oil. They refine crude oil, they get right from petrol to aviation fuel to diesel and the other lower fractions they sell. In a petrochemical refinery, I don't know how many of you have ever gone to a petrochemical refinery? No? No opportunity? Okay. Please see one. In a petrochemical refinery, there are a lot of gases that get evolved. Especially the gases which are of use from there is methane, which gets packed in cylinders along with mercaptan and sold as LPG cylinder to your house. It also contains lot of ethylene and propylene. Okay? Ethylene and propylene. Ethylene and propylene are used for making plastics. Okay? The biggest plastic production today is that of polyethylene, followed by polypropylene. In today's life, wherever you go, whatever you touch, whatever you buy, there will be plastic components. These plastic components, after doing research, have been designed in such a way that they can virtually replace all metal parts. Okay? Right from aviation industry to your regular automobile industry, if your grandfather has a car, old car, see that car and see a car today, most of the body is made from these plastics, especially polypropylene. So, you can make very hard materials from these gases. Okay? And this is a very lucrative industry because people will never abandon the use of plastics because they are not very expensive as compared to metal. Plastics, you buy a metal box and you buy a plastic box of the same dimension. The plastic box will be 1,000 times cheaper than your metal box. Even steel is very expensive nowadays. Okay. So, when I was a kid, those days, you know, you didn't have these backpacks. That was around somewhere between 45 to 50 years before. You had small suitcases which the kids used to carry made of steel because the plastic industry was not that developed. But today, every kid, a nursery kid can take a simple plastic box. The same suitcase now is in form of plastic. The cost is also much less, much less. Now, in today's class, I will give you an overview. We will not talk of polymer chemistry, certainly not, that is very involved, that is very advanced for you. Just a glimpse of how these plastics are made, the chemistry behind this. I will go as slow as possible. It is not your regular curriculum material because one of the mandates of your program here is that you should be told a little bit about advanced chemistry, right? So, most of the lectures here have been covered using regular chemistry, a little advanced, but this is a further little bit more advanced. Okay. Now, the first thing I want to know is how many of you understand what is a Lewis acid, a Lewis base? Hmm? Huh? Electron deficient compounds are called as Lewis acids and electron rich compounds is called as Lewis base. A Lewis acid is an electron acceptor, a Lewis base is an electron donor. So, here the entire, I will say, crux of the matter in this whole production of plastics is to use Lewis acids to activate some other type of organometallic compounds. What we are going to now go into deep into organometallic chemistry. You have had 2 lectures on that, right? One was 18 electron rule and all those things, and the other was some applications, some catalytic cycles. How many of you understood those lectures? How many of you did not understand those lectures? Tell me honestly. So accordingly, I will tune my lecture. I have not prepared anything and come, just some slides I got. It's more of a conversation that will happen rather than, teaching something which will go above your head. I don't want to do that. Whatever little you understand here is the most important thing for you. That is what you take home. Okay. So, this entire operations of making plastics was discovered around 55-60 years ago. So, let us see the earlier phases of what people did. Okay. In one lecture, I cannot tell you everything, but I will give you a very short summary of what is happening. Right? Now, you have heard of the Second World War? Are you aware of the Second World War? So, this Second World War time, Hitler got all the money from, mostly from chemical industries of Germany, right? There are companies like Bayer and BASF who were forced to donate a lot of money for fighting the war basically. So we are going to talk of something which was there at that point of time. People in the petrochemical sector those days were involved in trying to understand how to use this ethylene and propylene. They barely managed to get a procedure where they could separate methane, ethylene and propylene. First is to get the pure monomer, right? You understand what is a monomer? You understand what is a polymer, right? To make a polymer, you need a monomer. So, by the time they kind of only refined techniques, did some chemistry with these gases, but their interest was in trying to find out whether you can make plastics. Some preliminary evidences they got. But in 1952, you heard of Ziegler and Natta, right? Natta gave something which is called as, which gave birth to a concept called as metal carbon insertion. You heard of this? Insertion of carbon between a metal carbon bond. An organometallic compound has a metal carbon bond. Okay, that is the most primitive definition of that. There are certain metals where you can insert additional carbons in between this metal carbon bond. So, that is what this man reported, you take triethyl aluminum. You have ever heard of this compound, triethyl aluminum? Aluminum with 3 ethyl groups. You have heard of AlCl3, right? Instead of chlorine, instead of chloride ion, you are having C2H5. Let's not worry about how this is made and what is done. If you take this one and mix it with excess of ethylene gas at high temperature and high pressure, 100 bars is a lot of pressure. What you find is that this ethylene inserts in between the metal ethyl bond. M and O means that these coefficients can be different. It's not that if 10 units are there as M, N can be 8 units, O can be 5 units. They can all be different. All right. Then further on, this compound, you can use it to react with oxygen and you can make alkoxides. You have heard of metal alkoxides? Huh? Which alkoxide you know? Which metal alkoxide? Aluminum isopropoxide, aluminum methoxide, titanium ethoxide, zirconium ethoxide, niobium isopropoxide, niobium 5. So, same thing can happen also with main group metals. Your focus of chemistry in your textbooks is mainly with transition metals, correct? So, whatever you see in transition metals, most of the things happens also with main group metals, P block metals to be precise. Okay. So, here you can get alkoxide. Now, this alkoxide can be made to react with water. So, what happens is if you put excess water, you can make an alcohol. So, through this synthesis, I have told you how to make an alcohol from triethyl aluminum and ethylene gas. You have to tune the conditions in such a way that you are able to control this M and O fragments. Okay, is this clear? And of course, your side product is aluminum hydroxide, which further oligomerizes and gives you aluminum oxide. Now there is a second thing which happens. Once you get this compound, this can further react with ethylene gas, where you have raised the temperature. You see, from 110 degrees, now we have gone to 200 to 300 degrees. So, you have your vessel, you put ethylene gas, 110, something you formed, then you raise the temperature and you keep adding ethylene gas, don't stop that. Then finally, you get a compound like this. This is actually a terminal alkene. So, I have told you today how to make a terminal alkene and an alcohol from ethylene gas. Okay? Is that clear? Then what happens? Let us see. What is the mechanism of this? So, what you have done is you have made, see, in your last compound where you got a terminal alkene, you got different C2H5 units here, right? C2H5 units. So actually what you have made is a polymeric compound, where one of the a polymer has two ends, right? One of the N-terminal groups is a terminal alkene and the other one is hydrogen. So let us see this in a bit more detail. What happened here? How this was got? First I told you the observation. Now we will try to rationalize this observation. How this fact came. Just simply listen. There is no assignment for this lecture. I know it's a difficult lecture. Sit and listen. Okay? And if you want to write down something, you can. But try to understand what's happening here. That's more important. So you have taken basically the compound which I showed you, this one here, this one. Just look at this one, look at the structure. I am assuming here that this compound and that compound is the same, where M and O are different. Instead of C2H5, I am writing CH2CH2N H. So when this reacts with ethylene, you can get an intermediate like this. This, instead of O, we have written P, where this ethylene has again inserted. Here you see, this was M, now this is again inserted. This hydrogen remains from here. Understood? This is like organic chemistry. Let us write this as X. Now this can further grow. More and more ethylene, more and the second molecule of ethylene can insert here, third one can insert here, or it can keep on inserting on this direction. The chain keeps on building. You have aluminum, you have 3 arms there. The length of the arm increases, keeps on increasing. Okay? But at some point you need to stop the reaction. This cannot go on endlessly. If it goes endlessly, then you will be able to make some material which will not have any definite properties. Okay? So those times and how they optimize, we don't need to look at that. Now how do you terminate? Now when you have this one can self-decompose, giving you an aluminum hydride and an alkene. So you tune your reaction conditions again further, so that that XX intermediate begins to decompose. All right. So one of the central group gives you this one, and this aluminum takes up the hydrogen and produces this hydride. The same thing can happen with the other two groups also. So you will have a mixture of 3 different olefins. Right? What can happen is, this can give you a similar compound where instead of M you have N, and this can give you again, this part of the molecule can give you again another olefin where this is P. Instead of M you have P. So you have 3 different olefins, basically a mixture. Now why this was outdated or trashed is because there was no method available of how to separate them. When you do a reaction, a polymerization is also a reaction, right? This is not something arbitrary, right? You should be able to make a pure compound. You may get a mixture, but you should devise a method in which you are able to separate the mixture. These 3 olefins, polyolefins, had very similar properties, physical properties, very similar chemical properties, and separation was not possible. When can you separate two compounds. Either you separate them physically or chemically. Physically means that if there is a difference in solubility, you can dissolve one of the compounds in that particular solvent where it is soluble and the other one is insoluble. You can do a filtration. So, your filtrate will have the soluble fraction, the soluble compound, and the solid that you get is the insoluble part. That you can dissolve it in some other solvent. So, that is you are trying to separate them based on solubility. So, solubility is a physical property, isn't it? Now, chemically how do you separate them? I have two compounds, right? I do a reaction in which I can make a derivative of one of these compounds. Suppose if I have two compounds which are both soluble in all solvents. If I dissolve them in hexane, both are soluble. If I dissolve them in THF, both are soluble. If I dissolve them in any other solvent, both are soluble. Then how do you separate? Then you try to think of chemical separation. Now what you do is you try to think of a reaction where you can make a derivative of only one of those compounds. That means when you do the reaction with this mixture, only one of the compound react with that reagent. The other one remains as such. So, that means you have made a derivative. That derivative you can separate using physical methods. Do you follow? So, why I am telling you all this? So that these are all practical aspects of chemistry. These are more interesting than what we are actually trying to read at your stage for a child who is in school, right? It is not there in your books. I don't know, you are all from Tamil Nadu, right? And state board, correct? So, I don't know your books very well, but I know the NCERT books very well, but nobody talks about all this, right? So, let us see next. This particular hydride is called as a hydrido-aluminum compound, okay? Now, the interesting thing here is, in the previous slide, this has a tendency to decompose, right? Here you see, if I am able to collect the hydride, if I am able to isolate the hydride, again I put in ethylene gas, it gives me back a compound like this. So, at the stage of the hydride, you have two options, right? Either you terminate the reaction, where you get a mixture of 3 olefins, or you continue with the reaction, right? If you want to continue, this is the mechanism. If there are impurities in the system, self-termination can happen. So, once the self-termination happens, you get the hydride, but you have kept your pressure, other things constant. So, that hydride again reacts and gives you even further complicated mixtures. Okay? Now, how does the chain grow? You have your aluminum, one of the groups is C2H5. Right from the beginning, if we see, we started from triethyl aluminum, right? This is an electron deficient bond because of high Lewis acidity of aluminum, and this is an electron rich bond because of the pi electrons. So, a mechanism like this happens, and this is how this insertion happens. Now, the next molecule of ethylene can come in here, right? A similar thing can happen, and you can get finally something like this. Are we talking in the air, or you are clear about what's happening, or it's all going above your head? It's okay? That side? That side all girls? No boy wants to sit there? They are afraid? Now let's not worry about that. So why this method was not taken up further for, or not researched further? The primary constraint here was that from ethylene gas you got a mixture of different polymers, polyolefins. Could not separate those mixtures. So when you work with mixtures, invariably the properties, the physical properties of those mixtures do not match your expectations. I want to make a material of certain hardness, and I am dependent to make a polymer. So I have to make sure that I make a process where I get only one polymer, one type of polymer, not several kinds of polymers as a mixture. Then I will never be able to achieve that hardness. Okay? It's like 5 people staying in a big house. Always they are fighting with each other. All the strength is used to fight only. Okay? And they are not able to achieve the collective strength of the family. But then if you have one particular nuclear family where all the 5 people separate and live together, you will see in most cases their productivity will be much higher because they are not fighting amongst themselves anymore. Everything on earth is a constant. Even your body energy is a constant. You eat so much food, so much energy you get. How you use that energy is dependent on you. Most of that energy if you use for fighting, then you have a very limited energy to do your work. So at your stage, 3 important things. Like a father, I am telling you this. Don't waste time for unnecessary things. Put full 100% of, or close to 100% of your time for what you want to do. We have come very far that the government selected you based on your performance. Keep the performance alive. Okay? I want to see each of the kid here either in an IIT or in a NEET, something you should qualify, or some other entrance exams. That can only happen if most of your energy is used for doing in fulfilling your ambition. If you fight, half your energy is lost. Okay? So this is not relevant, but I am just giving you this as an advice. Like a father, I am telling you this. Okay, now you might have heard of Ziegler-Natta polymerization. You have heard of it, right? All of you have heard of it. How many of you know what it is? What exactly it is? Today we will see that, what exactly it is. Okay? Around 1953, Ziegler discovered that high polymers means high molecular weight polymers of ethylene can be obtained by the addition of a transition metal salt to an alkyl aluminum species, TiCl4 plus AlEt3 plus ethylene gas. You can get a really high molecular weight polymer. Single polymer, mostly single polymer, not 100%, 95%, 98%. In 1955, just 2 years, Nata, there were two independent people, Ziegler and Nata. Ziegler was a German, Nata was an Italian. They were working in two different countries without knowing that they are parallelly working together on the same problem. Okay. So, Nata reported the properties of highly crystalline polypropylene and other polyalpha olefins. Alpha olefins means at the alpha position you have an olefin. One of the, they are basically terminal olefins, to make it simpler, not internal olefins. Which have at least long sections of main chain asymmetric carbon atoms of the same absolute configuration. We will try to understand this a little bit later. So, you understand what is tacticity of a polymer? We will see that. We will go a little slow and see that. Let us first, so these were the reports actually, the original reports in those days, just to show you. The same thing can happen if you take TiCl3 and AlEt3. Transition metal salt, TiCl3, AlEt3 is a aluminum alkyl. Now, this is the structure of the alpha form of TiCl3. You understand by alpha forms and beta forms? I give you a crystalline material, alpha form, beta form, different forms of crystalline materials are possible, correct? At least this much you understand. Yes? Okay. That is enough for me at this point. So, you see, there are two different kind of titaniums, one on the interior, one on the outside. I give you some salt, right? Salt has particles in the solid state. So, there is a definite edge. If I put all the particles together, there is a definite edge and there is a different core. For each particle, there is a different edge, there is a definite edge and a definite core, right? Say I give you 5 grains of common salt, very tiny grains, you can't see, the one which you eat at home. Each grain will have a surface. The surface will have molecules of that salt. The core of that small particle inside will also have it, NaCl. Outside at the periphery also there will be NaCl. Inside the core also there will be NaCl. But it is not always true that they will have the same coordination environment. Okay? For NaCl they will have because it is a very simple molecule, it is a linear molecule. But when you take complicated molecules like TiCl3 etc., then it is not that what will happen on the surface, the coordination environment around the surface and that of the core will be same. They are usually different. Look here, each titanium has 6 neighbors, correct? And look at the edge, they have 5 neighbors. Are you convinced with this? How many neighbors does this one have? How many neighbors does the one at the edge? Say this one is the interior and this one is at the edge. 5. Pentacoordinate and hexacoordinate. Huh? This is penta, the blue one. Red is hexa. Why the blue one is penta? Because there is no neighboring titanium. Okay, it's at the edge. There is no neighbor to coordinate with. This creates the difference. So what happens is the penta one has one coordination number, one point of coordination it can accommodate. Usually transition metal salts are hexa coordinate. Can you tell me the reason? TiH2O 6 times 3 plus. H2O 6 times 3 plus. FeH2O 6 times 3 plus. I take iron chloride, FeCl3, I put in water, I'll have FeH2O 6 times 3 plus, and your counter anion will be your chloride anion. Why is this coefficient 6? Have you thought about it? Why not 5 or 4 or 1 or 2? Why is it 6? That is correct, partially correct. What is the atomic number of titanium? Huh? Can you write down the electron configuration? Do you go up to 3p, 6, 4s and 3d, right? Huh? 4s2, 3d, 2. So titanium 3 plus, you will have what? 3d1, right? So basically what you have 3d, you have 4s, or let us write this 4s first. 4s remains this one. Then you have 4p also, no? You have 4p also, right? 4p is also there, it's empty. So what comes after 4p? Think and tell me. You don't have to go that far. I think 4p should make it. You have 3d, no? 3d there are 5 orbitals. Sorry, they are not symmetric. This is 1, 2, 3, 4, 5. Right? One of the orbitals is where one electron. You are surrounded by water. Water has lone pair oxygen. So one lone pair gets donated here. Correct? Next lone pair gets donated here. Now you tell me, does it make sense? You have this one, no? So one of this has come here. Next water molecule I take, this lone pair has come here. Likewise. Now the question is why 6, why not 8? When you talk of symmetry of a system, nature is symmetric, do you agree? When you talk of symmetry of a system, what do you understand by symmetry? That wherever you cut the molecule, it should be equal. Suppose if you take 7 coordinate, will it be equal? If you take 8 coordinate, one of the geometries is dodecahedral. Coordination number 8, do you know the possible geometries? So what are the geometries? Coordination number 8, 6 is octahedral. Yes. Are they symmetric systems? Are they symmetric? Yes or no? Which one is symmetric? Tell me the geometries first. Coordination number 6 is octahedral. Coordination number 8, I am talking. 1%. Square antiprism. Is a square antiprism symmetric? There has to be a plane of symmetry, there has to be a center of symmetry. Square antiprism and what else? Which is easier to make? Octahedral or those? Octahedral is symmetric, easiest to make at this point. Of course, there are factors like hydration, energy and those things. We are not considering those to make it simple.
SwayamPrabha. Digital India. Educated India.